Welcome back to Introduction to Speech Understanding. The transcription doesn't seem to be working. Oh, now it's working. Good. Now let me share my screen. That seems to also not be for me this week. Here we go. There we go. Let's begin with, so last week we learned about the basics of automatic speech recognition. I taught you that there's a model and that there's a model of each of the different sounds that you can recognize, and that those models have to be compared with your test speech in order to see what sound is being produced at each time. This week, what I want to do is to cover the way of using speech recognition models if the speech recognition models are neural networks. So let's go ahead to Intro to Speech Understanding. Let's go to my local directory and let me do, as usual, let me fetch the data from Git, from the release. And then let me merge the release with the contents of my local directory while allowing unrelated histories. There we go. And now we should have a lecture 10 and a lecture 11 available to us. This week is lecture 10, so let's change directory to lecture 10 and start with Jupyter Notebook. All right. The reason I want to teach you a little bit about neural networks is that neural networks are the foundation for all of modern artificial intelligence. And so if you have any interest whatsoever in artificial intelligence, then you should know something about neural networks. This week, we're going to use neural networks in order to train and test automatic speech recognizer. It's finding, oh, I see. This should be Ahref. There we go. So here's a link to more information about neural networks on Wikipedia, in case you would like to learn about neural networks in general. We're going to first of all process the data, and then we'll train a neural network and test the neural network. Training any machine learning algorithm, such as a neural network, we need examples. So the input will be a vector x1 and the output will be y1. X is what the neural network receives as its input, and y is what it wants to generate as output. So for example, in automatic speech recognition, X would be a speech waveform, and Y would be the text that you generate as the transcription of that speech waveform. Let's load the same training audio that we used last week, train.m4a. I can load that using Librosa. And then I'll calculate a wideband speech spectrogram of that speech. You remember that this is the vowels a, e, u, a, o produced in my voice. And you can replace this with audio of your own voice if you'd like. I've created a wideband spectrogram by setting the length equal to 4 milliseconds. The window skip is 2 milliseconds. And then I calculate the magnitude short time Fourier transform of the pre-emphasized speech. Note that I'm subtracting speech of m to m plus l is being subtracted from speech of m plus 1 to m plus 1 plus l. So I'm pre-emphasizing the speech spectrum. And the result is an image, a 2691 by 16 image. So there are 16 different frequencies. and there are 2,691 frames in this audio file. Last time, we first divided it into segments and then classified each segment. This week, I want to do something a little bit harder. This week, I want to try to classify every single frame. And you'll see that it sometimes makes mistakes on a single frame while still getting the majority of frames correct. I'm going to try to create a reference label such that all of these frames that are silent should have the label y equals 0. All of these frames that are the vowel ah should have the label y equals 1. All of these frames that are the vowel e should have the label y equals 2, and so on, all the way up to the vowel o. Every frame which is an example of the vowel o should have the label y equals 5. And so I can do that using the voice activity detection that we discussed last time. I'll create an energy vector, which is just the sum of the squares of the samples in each frame. I'll use a longer frame, in this case, a 25 millisecond frame length and a 10 millisecond frame skip. So the frame here corresponds to 5 times the duration of the original frame. And for each of those frames, I'll calculate a 1 if the energy is greater than 10% of the maximum, otherwise a 0. And then I'll set the start frame to be places where the VAD goes from 0 to 1. The end frame are the places where the VAD goes from 1 to 0. And then I'm going to go through and label each of those segments as either 1, 2, 3, 4, or 5. Right, so I'll go through and label start will be labeled with the label 1. Start frames of 1 to end frames of 1 will be given the label 2, and so on up to the label 5. In this way, I create labels for every frame. And notice that I'm taking 5 times the start frames and 5 times the end frames. This allows me to map from the VAD, which has a frame skip of 10 milliseconds, back to the spectrogram, which has a frame skip of 2 milliseconds. So by upsampling by a factor of 5, I get a total of 2,691 frames, exactly equal to the length of the original spectrogram. Now I have my input vectors, x, which are the speech spectra, and my output integer, y, which is a number between 0 and 5. So now I have the training data for my neural network. And now what I want to do is I want to train the neural network. Basically, the neural network will calculate a vector, a model vector for each of these vowels separately. There will be one model vector for ah, one for E, one for U, one for A, one for O, and also a model vector for silence. The way that I'll do that, though, I'm going to introduce you to the toolbox called PyTorch. And the reason is that PyTorch is the standard toolbox for training and testing artificial intelligence. If you're interested at all in artificial intelligence, then you probably want to run some experiments using the PyTorch toolbox. There are excellent tutorials available online for PyTorch, and I recommend that you do any of those tutorials if they're interesting to you. First of all, you need to install PyTorch. If you haven't installed it previously, you can install it by using exclamation point and then pip, and then install Torch and Torch Vision to install those two things. Now, the neural network that I'm going to compute is exactly the same similarity metric that we used last class. Last class, I introduced you to this cosine similarity, which is the cosine of the angle between the vector x and the vector w. And that cosine is calculated by taking the dot product between x and w and dividing it by the length of the vector x times the length of the vector w. Right? We can do this using 2 layers. First of all, the layer norm layer takes the input vector x and divides it by its own length, so that the total length of the vector x over x norm it's a unit length vector now. So that's what a layer norm does. A layer norm is listed here. It's a normalization that computes an output which is equal to the input minus its expected value divided by the square root of its variance. So the result is something that has an expected root mean squared value of 1. So that's the layer norm layer. And next, we'll compute a linear layer. And the linear layer takes that vector x and multiplies it by a matrix A, where if we train it, it's possible for the matrix A to learn the values W0 over the norm of W0, all the way up through W5 over the norm of W5. These W vectors are the model from last time. So W0 should be the shape of the spectrum for silence. W5 should be the shape of the spectrum for the vowel O. And each of these vectors will be dot producted with x and then divided by the length of x times the length of w. In training a neural net, however, we don't require that it has to converge to this solution. We start with random values for the matrix A, and then we train it over several iterations of training until it learns the optimum value for the matrix A. So we'll initialize it by importing Torch neural networks, and then I'll use Torch neural net sequential, which takes several layers one after another and composes them into a single model. In our case, the model will have two layers. The first will be a layer norm, which normalizes the input vectors to have unit length. The input vectors have a length of 16. Why do they have a length of 16? The reason they have a length of 16 is that the spectrogram has 16 frequencies, right? There's only 16 frequencies in this spectrogram, so the input vector will have a length of 16. Then the linear layer will take that input vector of length 16 and multiply and generate an output which has a length of 6. Why is the output length of 6? Because there are 6 different possible labels. Silence, A, E, U, A, O. Right? So there will be 6 different columns. The matrix A will have 6 rows. Each row is the W vector corresponding to a different output label. Those output labels are silence or A, E, U, A, O. So this linear layer will have an input size equal to the length of X and an output size equal to the length of Y. We can create that initial layer and we can print out the model, and the resulting model is just a layer norm input layer and a linear layer which has input features 16, output features of 6. Let me see if I remember. The model 1 will be the linear layer. And we see that the linear layer has input features 16, output 6. And I think that if I want the parameters, I just type parameters. Yeah. Okay, it has no, how about params? There's some way to find the actual input matrix. Um, oh, parameter. Let's try that. No. Let's try the documentation. Let's try the get started documentation. And we want the introduction. Hmm. I guess I'm not going to be able to find. There's a way that you can print out the values of the parameters. Um, the linear layer includes a matrix A. It includes a 16 by 6 matrix A that is initialized randomly, right? I say that we want to learn this value of A, but initially the values are going to be completely random. And what we're going to do is we're going to take those random initial parameters, 16 by 6, and we're going to try to learn them. And the way that we learn them is we want to train it to minimize the cross entropy between the correct labels and the outputs. The cross entropy is the negative log probability. So if we minimize the negative log probability, that means we're maximizing the log probability. That means we're maximizing the probability of the correct label. If the correct label is y, then we want to maximize the probability that y is equal to k, given the input vector x. The neural net calculates this probability using what's called a softmax function. The softmax function takes e raised to the zk power divided by the sum from I equals 0 to 5 of e to the zi. So this output is sums up, but it's always a positive number, and this positive number sums up to 1 if we add across the different possible values of k. So adding up p sub k from k equals 0 to 5 adds up to 1. Right, so we want to try to minimize this cross entropy because we want to maximize the probability that the neural net gets the correct answer. We do that by, first of all, initializing. We choose a loss function. We'll choose the cross entropy loss. We'll say that we want to maximize the probability of the correct answer. That means we want to minimize this cross entropy. Second, we'll choose an optimizer. Optimizer performs a form of gradient descent. Gradient descent is this kind of operation. So if we look at gradient descent as a video, we see that all of these different dots are being randomly initialized. And after random initialization, they move downhill, right? In this likelihood diagram, here are areas that have high loss, shown in yellow. Here are areas that have low loss, shown in blue. And it moves downhill from the high loss area downhill to the valley. Right? So think of this as an area that has very high value of that loss. We want to move away from that toward a value that has a low value of the loss. High cross entropy, low cross entropy, low probability, high probability. We want to move from a set of model parameters that have low probability to a set of model parameters that have high probability. And we do that by starting with any value of the parameters and then just gradually moving downhill, right? We just gradually adjust the parameters over several iterations. We iterate over and over again and gradually reduce the reduce the cross entropy. So in our case, we're going to use the ADAM optimizer. ADAM is a particular kind of optimization based on gradient descent. You can look up ADAM in PyTorch here. We see that the ADAM optimizer, well, there's a lot of complicated details. It involves the learning rate gamma, two adaptation parameters, beta 1 and beta 2. The set of parameters that you're trying to optimize, theta, this is in our case the matrix A, the linear parameters of the linear layer, and those have to be updated step by step. So for t in each of the iterations. In our case, we're going to do 1,000 iterations for t in the range from 0 to 999. And for each of those iterations, we'll run our model on the spectrogram. So we'll take the spectrogram, we'll create from it a PyTorch tensor with a data type float, and then we'll run the model in order to calculate the output samples z. So the output samples z are, we can show them here. Z sub k is equal to the dot product between the matrix W sub k and the matrix X divided by, well, actually, it's just that dot product because W sub, well, yeah, divided by the norm of X times the norm of WK. Right, so Z sub k is WK transpose X times WK dot multiplied by X. That's the same thing as saying that the vector Z is equal to the matrix A multiplied by the vector x divided by the length of the vector x. So we have that z is equal to the matrix A multiplied by the vector x divided by the length of the vector x. Remember, this first division is done by the layer norm layer, and then this second matrix multiply is done by the linear layer. So we take z sub k, then we calculate the z vector using the forward propagation in the model. So that's here. We calculate this z vector by applying the model to the spectrogram. And then we calculate the cross entropy loss, which is the difference between the output of the model and the desired labels. This calculates the loss function, which is the cross entropy. It's this negative log probability. We want this loss spectrogram, and we'll keep one of its values as the loss values of t. Loss values will show the cross entropy as we progress through time. And then we will zero out the gradient for the optimizer and then calculate what the backward does is it calculates the gradient in this gradient that I showed you. Gradient descent. In this gradient descent, remember that we have to find the direction to travel for each dot. And then once we find the direction to travel, then we have to move the dot. So in every iteration, we have to find which direction should we change the vector. And then we take a step in that direction. So first of all, we find the model outputs. We compare the model outputs to what they should have been. Then we find the direction in which the model parameters should be adjusted, and then we take a step in that direction. So here's complete training. We've defined the loss function, we've defined an optimizer, and then for every iteration, we find the model outputs, we find the difference between the model outputs and what they should have been, we zero out the gradient and then compute the gradient, and what is the direction in which the model parameters should be adjusted, and then we take a step in that direction. And if I run the optimization for 1,000 iterations, then we can see how the loss starts out with a cross entropy more than 2 and gradually decreases to a cross entropy of less than 5. Let's see, the cross entropy is the negative log probability. So that means that the log probability starting out at -2, meaning that the probability of the correct answer is less than a quarter. And the log probability is increasing to -0.5. That means that the probability of the correct answer is increasing to the 1 over the square root of 2. Right, so the probability starts out at e to the -2, and the probability increases to e to the -0.5, which is pretty good. We can find out how well it worked on the training data by calculating this softmax. The softmax of z sub k is this probability, p sub k. Right, so if I calculate, here's z, I apply the model to the spectrogram, and then I can take that spectrogram and plot the spectrogram first, and then take the softmax of z. So I'll take z, apply the softmax to it to convert it into a probability, and then apply detach and numpy to convert it from PyTorch into NumPy format. And the results look something like this. Here's the original spectrogram, A, E, U, A, O. And here are the different output probabilities. You can see that silence has the highest probability during most of the silences, but not all. There's this one section in here during the silence when the spectrogram looks more like an A than it looks like the spectrogram for silence. Similarly, the ah looks mostly like an ah, but there's a few frames that look more like O than they look like ah. The E looks mostly like an E, but there's a few frames that look more like silence, and there are a few frames that look more like A. The U looks mostly like U, but there's a few frames that look more like O. The A looks mostly like A, but there are a few frames that look more like E. And the O looks mostly like O, but there are a few frames that look more like ah or E, right? So A is kind of halfway between ah and E. So you can see that in general, the output probability is strongest for the correct vowel, but not always. Sometimes the output probability changes so that it's a little bit closer to one of the other vowels instead. What we really want, though, is not to recognize our training utterance. What we really want is to recognize test utterance. We want some testing utterance which is different from the initial training data, and we want to be able to input some test utterance and recognize its content. So here's an utterance E-A-U-A-O. We'd like to be able to run that same neural net recognizer that we trained using these data. We'd like to be able to recognize this test utterance. So I'll calculate a test spectrogram by calculating the magnitude short time Fourier transform and then taking its logarithm. Right. So here's the test spectrogram of E-A-U-A-O. Here's some noise at the beginning. This must be where I breathed in. There's the E-A-U-A-O. And now let me just apply the model to it. I convert this spectrogram into a PyTorch tensor with a data type of float. I apply the model to that spectrogram, and I get some results. And now I'll take those results and I'll compute their softmax, and I'll detach the softmax and convert it to NumPy, and then transpose it so it's an image. And the resulting test probabilities are mostly correct, but sometimes not. E-A-U-A-O. You can see that this is pretty good, except that the U is not very strongly different from an O. The O is mostly O-like, but the U is really very hard to distinguish from an O, according to this single frame emphasis. And that's a neural network. We now have a neural network that consists of one layer norm and one linear layer. The layer norm, remember, computes an output, which is the input divided by the square root of the variance. The linear layer then makes the dot product between the input and the output. So if we go back to neural networks, a neural network then is some model like this. We have our input layer, we compute its layer norm, and then we multiply it by a linear layer to compute the output. And that's the whole thing. That's the whole neural network. Let's do our homework. The homework this week consists of 3 functions, not homework 9, homework 10. So let's import homework 10, and the first function is called getFeatures. We want to take an input waveform with a given sampling rate and generate from it a feature matrix, which is the spectrogram, pre-emphasize the signal, then compute the spectrogram with a 4 millisecond skip frame length and a 2 millisecond skip, and then keep only the low frequency half. Let's do that part first. So the first thing we want to do is we want a frame length, which is a 4 millisecond skip, millisecond frame length, sorry, and a 2 millisecond skip. And from that, we want to compute a spectrogram. So first we want the magnitude short time Fourier transform of the short time Fourier transform, which is we take the speech frames m plus 1 to m plus 1 plus L minus speech of m to m plus L, because we want to pre-emphasize it, for m in the range from 0 to the length of the waveform. This should be waveform, not speech. For m in the range from 0 to the length of the waveform minus the length of the frame, with a skip equal to S. And we want to take the FFT along the row axis and then take its absolute value. Then we want the spectrogram. The features will just be the spectrogram, which is 20 times the log base 10 of the maximum of 0.0 times the max of the MSTFT or the MSTFT itself. Now we have features. The features will be n frames by n feet, so it'll have a number of rows equal to the number of frames and the number of columns equal to the number of features. But oh, the number of features should just be the lower half. It shouldn't be all capital L of them. It should be L over 2. There we go. The second thing we want to do is to calculate the labels. We want a NumPy array of integers where we want the voice activity detection with a 25 millisecond window and a 10 millisecond skip. So let's compute those. We want the frame length to be 0.025 times fs, and we want the frame skip to be 0.01 times fs, right? 25 millisecond length, 10 millisecond skip. And then we want to calculate the energies of the speech frames. And this time we don't need to pre-emphasize because we're just calculating energy. And we want to take the sum again along the row axis. There we go. Now we have the energies. Now we can calculate the VAD. The VAD will be one energy is greater than 10% of its maximum. Otherwise 0, or m in the range equal to the length of energy. There's something I missed. Oh, just the closing. There we go. The frame starts will be the VAD that changes from 0 to 1. And the frame ends will be the frames where it changes from 1 back to 0 again. Now we have the beginning and the end of each frame in the VAD. Now we need to multiply them by 5 in order to get the labels. So we'll set labels will be all zeros unless we change them to something else. So we'll start out with the labels equal to NumPy zeros with the number of frames in the features. And then we'll change them for label in range from 1 to 6. Actually, let's just explicitly list the labels. We want labels 1, 2, 3, 4, and 5. We'll take labels from frame starts of label -1 to frame ends of label -1 equals the label, but we need to then multiply by 5 because of the difference between the VAD and the spectrogram. So from 5 times the frame start to 5 times the frame end, we set it equal to that label. And that should give us the whole set. Now we just return the features and the labels. Right, so we need to, this is just the pre-processing, right? This is just taking the input speech and converting it to a spectrogram and also labeling it. labeling it as either 0, 1, 2, 3, 4, or 5. Let's see if that gives us reasonable results here. We want to reload homework 10 and then show the spectrogram and the labels. And I've got a typo. I typed framens instead of frame ends, I guess. Frame ends. And here I have friends. Frame ends. Let's try it and see if that works now. There we go. Now we have the spectrogram, A, E, U, A, O, and now we have the frame labels, all 0, and then it changes to 1, and then 2, and then 3, and then 4, and then 5. So we have all of the frames correctly labeled. Now we have training data that we can use to train our neural network. Training the neural network, we'll use PyTorch. What we want to do is take an input feature matrix and a label vector and return a trained model and a set of loss values. All right, to do this, we're going to need to copy some code from what we've got previously up here. How did we train the neural network? Well, we started out by creating a loss function and optimizer and then training it over some period of time. Let me just copy that code over. Train neural network, I want to get rid of the runtime error. And I want a loss function, which is the cross entropy loss, an optimizer, which is Adam optimizer, a sequence of loss values, which is zeros equal to the number of iterations. And then for t in the range up to the number of iterations, I want to take the input feature matrix and convert every feature vector in that feature matrix, pass it through the model to create an output z vector, and then compute the loss by comparing the output of the neural network to the desired output, the labels that I was trying to obtain. I'll take that loss item and add it to the loss values, and then I will use that loss item to calculate the direction in which the parameters should be updated and to update the parameters. And what I want to return at the end is the trained model and the set of loss values. Right, so this is similar to what I just did in the lecture part of the course. I train a loss function, specify a loss function, specify an optimizer, and then for each iteration, compute the model in the forward direction, calculate the loss, zero out the gradient, take the derivative of the loss with respect to the model parameters, and then take a step in the direction of the downhill. Let's go down here to the homework and see if that all worked without any errors. The name model is not defined. Oh, I needed to create the model to begin with. The model was equal to torch neural network sequential with a torch neural network layer norm. Let's go look it up. We had torch neural network sequential with a torch neural network layer norm and a torch neural network linear. And 16 is supposed to be the number of features in the feature matrix, and 6 is supposed to be the number of distinct values in the output. So let's just make sure that we get that correctly here. Number of frames and number of feet. That's equal to the shape of the features matrix. And then I can convert 16 to n feet. And this 16 is equal to n feet. And then I also want to find out what is the largest integer in the labels matrix. So the number of distinct labels is equal to the maximum value in the labels matrix plus 1. And let's make sure that that's an integer. So I'll take the maximum values in the label matrix, add 1 to it, and that gives me the number of distinct labels, which I should specify here by the number of labels. I think that's everything I need. Let's try that and see if that's enough. Let's go down here to the homework 10.2, and let's try running that and see if that's everything. All right, good. Now we have a fully trained, we show the output loss values as a function of the iterate, and we see that the loss is decreasing from around 2 to around 0.5. And now we also have at the output a model. So now let's try testing our model. Now we want to take an input feature matrix and apply the model to that input feature matrix and return a matrix of probabilities, an n frames by n labels matrix of probabilities. So again, we want to go back to the sample code. The sample code here said that test results should be the model applied to the input feature matrix. And also now I need to convert that to a matrix of probabilities, which should be a NumPy matrix. I want to use detach NumPy, convert it to a NumPy matrix. The input is not test sgram, the input is the features matrix. And that features matrix is converted to PyTorch with a data type of float. And then we apply the model to it to generate the test results. And now we need to convert those test results to probabilities. Let's see how we did that in the code. We did that by taking those test results and computing the softmax and then detaching them and converting them to NumPy. So let's copy this part of the code over. The probabilities are the test results passed through a softmax, then detached and converted to NumPy. And what I want to return to the user here are the probabilities. All right, so now I've applied my neural net model to the input features. I take the features and pass them through the model, then pass the results through a softmax, and then detach them and pass them back to NumPy. Let's test that and see if that was what we needed. Okay, let me try running homework 3 dot test neural net and generate the probabilities. And here we have the spectrogram, and here we have the ASR output probabilities. And yep, that looks about correct, except that I didn't make my figure size. I didn't make my figure to be layout tight. I think this is a string. All right, there's my test spectrogram, and there are the resulting output probabilities, E, A, E, A, U, A, O. Let's check to make sure that that matches all of the grading criteria, and if it does, we can upload it and get the results. Ran 3 tests in 4 seconds, and the score was 100%. Excellent. So let's use GitHub Desktop in order to check it in and then upload it. We'll commit those 2 files to main locally, and then we'll push them to the origin. Takes a little bit longer this time because I need to upload both of the waveforms, as well as the complete PyTorch notebook. Let's go ahead and check on GitHub to make sure that that got checked in correctly. Let me switch from my teacher account to my student account. And let me check to make sure that lecture 10 got checked in correctly here. Lecture 10 has my homework, which does indeed have all of the changes that I just showed you. So I can take this and copy it and submit it to the course. And I don't have a homework 10 here, so let me go ahead and create one. Let me show you how I create a homework in Canvas. This will be assignment homework 10. And I'm going to ask you to please enter the URL of your copy of homework 10. And let's change the settings. Instead of having it be due tomorrow, let's have it be due on February 28th. And we'll change it so that you can try as many times as you like, and your graded, the version graded will be your last attempt. Um, there should be a button here to allow me to enter these settings. Attempts, last attempt, points 100. No, I don't want to cancel without saving. I want to save that. I wonder if it's hidden off. Oh, there it is. There's the save button. It's taking time. My internet connection is so bad. And now let me change it from visible. And now it should be visible to you. You should be able to go to Canvas and enter the URL of your copy of Homework 10. That's all for this week. Let's go ahead back to the home page here, and let's take attendance. So let me go to the campus plan web menu. And go to web attendance registration. And I always forget which one of these it is. I think it must be the latter one. 2025, December 8th. That sounds right. Okay, please go ahead and I will stop recording.